Log on, tune in, find out. Another good idea from Cambridge.
Good afternoon. Before I get started, I just want to say that lots of people have asked me for slides. They're available at the following address. Right now, it will ask you to enter a password, which is Principessa, and you have the address right there. Okay, so if you want to retrieve the slides, they're of course available, and that's where you can find them. So it's http public.me.com / Jean_Dennis with one N. And so you've got 7 lectures already. We all good? Okay, all right, so today this is where we are in the lecture series. This morning we talked about matrix completion, a new kind of problem. We're going to extend this work today. We're going to talk about robust principal component analysis, and then I will try to say some things about numerical optimization, but unfortunately not a whole lot because of time constraints. Okay, so the agenda for these lectures, I'm going to introduce a separation problem, which has some flavor with what we discussed this morning. I'm going to try to motivate why this is an interesting problem. I'm going to present you some theory. I'm going to show you lots of applications in computer vision if the projector is cooperative, and then I'm going to discuss some computational aspects of all of this. Okay, so the problem. Before I get started, I want to say that this is joint work with Zhao Dongli, grad student at Stanford in math, Ima and John Wright, who are 2 computer scientists working at Microsoft Research Asia, and they're just wonderful. All right, so I'm going to introduce a separation problem, and you'll see that as pretty much everything stated in this lecture, this is a very simple problem to state. And the problem is this. I've got a matrix that I get to see, and it's a superposition of a low-rank matrix and a sparse matrix, which is pictorially represented this way. It may not be the best pictorial representation because it seems like a low-rank matrix is an easy guy, but it's not. But all right, anyways, this is a low-rank plus sparse. It's a sum of a low-rank plus a sparse component. All right, I get to see the data matrix M. But I do not get to see the low rank component, which from now on we're going to call L like low rank, and I do not get to see the sparse component, which I call S. Okay, so L naught will be our low rank component. It's unobserved. S0 is a sparse component. It is unobserved. I just get to see their sum. The problem, as you can imagine, is that's the one I need to use. No. The problem, as you can imagine, is to recover their sum, which seems really daunting because I just get to see A plus B. I want to recover A and B. So it's like asking, sorry. Is this working now? Yeah. All right. The problem seems daunting because it's like you observe the sum of 2 numbers. I want to know what are each of these numbers, and it seems impossible. But I claim that if we could do it, that would be great. And why would it be great? It would be great because, well, maybe I'll explain it statistically. It would be great because this is, in many problems, we are given data, which is, we would like to reduce dimension essentially. You give me a large data set. I want to essentially reduce dimensions, but this data set may have been corrupted, and that's what I need to deal with. And so to introduce a problem, I'm going to talk to you about classical principal component analysis very briefly and tell you why, what the shortcomings of principal component analysis are, and then I think that will be a very clear motivation for what is it that we're trying to do here. Okay, so classical principal component analysis is something that looks like this. I've got a data matrix M, which is a superposition of a low-rank component and a small perturbation. So the way statisticians think about principal component analysis is that you give me a data matrix. I think about the columns. The columns for us are variables. And these columns are correlated, which means that they span or near a low-dimensional space. And the problem is to try to recover this low-dimensional structure, to extract low-dimensional structure from data. So I've got a low-rank matrix plus a small perturbation. So I have column vectors that are approximately near a low-dimensional space. And I would like to essentially recover this low-dimensional space. And the way we do this, of course, as everybody knows, is through principal component analysis, which is the main tool for reducing dimensionality in large data sets. And the way this works is we're going to try to find a matrix L, which is closest to M in some sense, and has a rank which is bounded by K. It sounds like a hard combinatorial optimization problem because what we argued this morning is minimizing under rank constraints is almost impossible. But in this very special case, it is not hard because we know that we get this by the truncated singular value decomposition. So the solution to this problem, and that is the only rank problem I know how to minimize, is given by the truncated singular value decomposition, where I take the singular value decomposition we've seen this morning, and so the best rank K approximation simply keeps the largest singular vectors in this expansion, throws away the rest. This is a fundamental statistical tool that we teach every undergraduate at Stanford. It has an enormous impact in applied science, as everybody knows. What we teach a bit less about principal component is something like this, which is that it's extraordinarily sensitive to outliers. So let me try to make this point quite precise. Suppose that now you give me points, columns, and again, because I can only draw in the plane, I'm going to put these points on a line, and so they span a low-dimensional subspace like this. And if I, of course, find the first principal component, the first eigenvector of the covariance matrix, or the first singular vectors, if you will, I'm going to get this line, of course. But suppose that this point, which is here in blue, has been incorrectly recorded. So that the sensor failed, something went wrong, and instead of being here, this blue point is right here. And now I just use the same approach. I compute the largest singular vector, and I draw the best linear approximation I can, and I'm going to get this red line. And this red line has obviously nothing to do with the low-dimensional structure. So what are we discovering here? That one corruption, one single entry in your matrix is wrong, and the whole structure collapses. Okay? Just like least squares, principal component analysis is extraordinarily sensitive to bad corrupted data points. It is not robust in any sense. And that is a bit of a problem because as we're dealing with larger and larger data sets, gross errors frequently occur in many applications. In image processing, people want to essentially reduce dimensions to perform tasks such as subject classification and things like this. But in those data sets, you could have varying illumination conditions, you could have people wearing sunglasses, you have bad things happening, which means that if somebody is wearing sunglasses and you try to project them, they're not going to be ending up where they need to end up. So in image analysis, we've got enormous errors due to occlusions. In web data analysis, we have to deal with the fact that people tamper with data. In every field that I'm familiar, we have to do with sensor failures. Gross errors occur all the time, and that needs to be addressed. So, okay, so that's the problem we're looking at, and of course, what I want to recover is the low-dimensional structure when somewhere in this data matrix, maybe quite a high percentage of the data entries are completely unreliable, but I would not know which one. Okay. All right. And so the goal is to recover. So I have a low rank matrix, but it's been corrupted by by a sparse component, so I get just the sum, so take S to be, think of it as being impulse noise, then if we could actually separate, if we could actually recover the low-rank component and the sparse component separately, if we could actually perform this blind deconvolution very well, then I would be able to recover the low-dimensional structure in the face of very gross errors. Right? So that I could do what we call robust PCA. Now, of course, in my application, the informative components may be either the low-rank component or the sparse component, and that depends a bit on your application. So, for example, in video surveillance, which is an application that some people care about these days, what you've got is you've got here frames taken in an airport, and what you would like to do is you would like to separate the foreground from the background. Okay, so you want to detect any activity in the foreground, for example, which would be these people moving about the airport. So you want to kind of do background subtraction. And what you can think of this is you can think of this as a separation problem, because if I were to store the images as columns of a large data matrix, then of course the background is not changing very much. It's changing because of illumination conditions changing. And so I'm going to have a very low rank background. And about this background, I have people moving, so I have a sparse disturbance in this low rank landscape. And so if I could perform the separation, I could perhaps actually find the foreground, because I can probably model the background as a low rank component. Okay. We deal with this because of the problem we mentioned this morning, which is a Netflix problem that I discussed before. It's a bit more subtle than what I just discussed this morning, because we have users tampering with data. Don't ask me why, but they're users who enter ratings that have nothing to do with their preferences, and that's something you have to deal with. Okay, so this would be considered to be gross errors in your matrix, and so in the Netflix problem would be even more challenging, that you have few samples of which a fraction are corrupted. Then what do you do? Okay. There are many other applications that we discussed this morning. There are applications in graphical modeling, there are applications in system identifications, and many, many more applications. For us, the main application is to be able to recover low-dimensional structure from badly corrupted matrices. Okay. So I'm going to talk about the theoretical aspects of this problem first, and then in the end, I'm going to show you some applications and some computational aspects. But let's look at the theoretical aspects. All right. So I've got this matrix M that I get to see. It's the sum of an unknown matrix, which is L, which has, I know nothing about it. I don't even know its rank. And a sparse matrix, which I know nothing about. I don't know how many entries are non-zero in S. I don't know their locations. I don't know their magnitudes. I know nothing. To recover this matrix, we're going to propose a very simple algorithm, which for the purpose of this talk, we're going to call the principal component pursuit algorithm, which has a flavor of things you've seen this morning and of course during the first 3 days, which is that of course there are infinitely many matrices L and S such that their sum is M. But among all these decompositions, I'm going to pick up a special one. I'm going to pick a decomposition such that the nuclear norm of L plus a scalar lambda times the one norm of S is minimum. So we've seen all these norms already. The nuclear norm is simply the sum of the singular values, which we discussed heavily this morning. It's somehow a convex proxy for the rank functional. The one norm is it's a bit of an abuse of notation. Yes, it is. Yes, it is an abuse of notation because I'm going to see S as a gigantic vector and just calculate the one norm of the vectorized version of S. Okay, so, well, it's just a sum. The one norm of a matrix for me in this talk is the sum of absolute values. Okay? All right. So, the L norm, the nuclear norm is a true matrix norm. It understands that L is a linear transformation. The other one is not. Okay. All right. This was also proposed by Chandrasekaran, Sanghavi, Parillo, and Wilsky in 2009 at the same time, maybe a bit before. The surprise here is that under very broad condition about L naught and S naught, even though I know nothing about them, this program succeeds. That is, it recovers the low rank component exactly and the sparse component exactly. Okay, and so the goal is first to explain what these broad conditions might be. But that's where this talk is, of course, linked to what we've heard this morning, which is that, well, if you prepare a matrix that is both low rank and sparse, obviously this problem has no meaningful solution. So this is a guy we've seen this morning. It's you prepare a matrix M like this, and you give it to me, and I have to extract from it its low rank component and its sparse component, and that's going to be very difficult because this low rank matrix is both low rank and sparse. And so we cannot have a matrix which is low rank and sparse. In such a situation, the problem makes absolutely no sense, and so we're going to have to put some conditions for identifiability. So the conditions we're going to put on the low rank part are exactly what we've seen this morning. How many people were not here this morning? So like, I don't want to kind of a few people. So I'm going to have to kind of go over this. Okay, so we have the low rank component, which we're going to see through its singular value decomposition, and we're going to require an incoherence condition about its column space and its row space to prevent it from being too sparse. And so we're going to introduce this coherence parameter mu, which quantifies the maximum correlation between the basis vectors and the column and the row space of the matrix. Okay, so what we have here is we're saying that mu is the smallest number I can find, such that for all basis vectors EI, their projection onto the column space is bounded by mu times the dimension of the subspace onto I'm projecting onto, and the same thing for the row space. Right? So what we've argued this morning is that if mu is kind of small, these subspaces are not aligned with the coordinate axis. If mu is large, they become highly collinear, and if they become highly collinear, the low rank component might look like this. Right? So mu is just a parameter that quantifies the degree of collinearity between the column space and the row space of the matrix and the coordinate axis. And obviously, if mu is too large, then the matrix could look like this, and there's no way I can perform separation. So we're going to introduce this parameter mu that quantifies the degree of correlation between the basis vectors and the column space and the row space of your matrix. Right? So what we've seen this morning is roughly a condition like this, means that the singular vectors of your matrix or the principal components of your matrix are not sparse. Because if they were sparse, it's always the same story. The low rank component could be like this, and the problem makes no sense. Okay, so we're going to assume some kind of incoherence condition of this form. That's the only assumption we're going to make on the low rank. Everything is deterministic. I just quantify the degree of correlation between the coordinate axis and the column and row spaces, and we'll see that the theorem depends on that number. Now, is this enough? No, of course it's not enough, because now let's say that we have a low rank matrix which is not well aligned with the coordinate axis. Suppose that now you're very devilish, and what you do is I prepare a low rank matrix, but Emmanuel, being very devilish, take its first column and subtract it. Right, so suppose I create a sparse matrix which looks at all the entries in the low component you prepare, and I'm just going to subtracting, I'm just going to do send you the difference. So what I've done is I've carefully erased all the information in the first column. I've reduced the rank, at least I did not increase it. And so I ask you to recover this matrix, to recover the sparse component. It's not going to be possible. Okay, so if you're allowed to adversarially select a few entries that you want to corrupt, then by touching, for example, entries in a column, you can actually corrupt a low rank matrix in such a way that the information is not recoverable by any method whatsoever. Right, so just like as this morning, we're going to assume that yes, you can corrupt lots of things, but we're going to assume that these corruptions occur at random location. That is the only place where randomness enter in the theory. That you can corrupt any way you want, but first the entries that you can corrupt are selected at random. And so result that you're about to see will hold with large probability, and the probability is over the locations of this of this corruption pattern. Okay. All right. And now the result is this. We have a low rank matrix, which is n by n, of rank essentially n over log n squared. And if you have high coherence, then the rank will have to decrease. So of rank n over the coherence times log n squared. But if we think that the coherence is 1, for example, of rank n over log n squared. But you see the role played by the coherence. Right? So we have a low rank component of rank roughly n over log n squared. I corrupt a random fraction of the entries, a constant fraction of the entries. So each entry has a positive probability of being corrupted. Then with very high probability is this very simple algorithm which has minimized the nuclear norm plus 1 over square root of dimension times the 1 norm is exact in the sense that the solution to the optimization problem is exactly the low rank component, and S hat is exactly the sparse component. This is stated for square matrices. The same theorem is absolutely the same for rectangular matrices. All what you have to find to replace is n by the maximum of the dimension. In particular, the lambda that you use to adjust it is 1 over square root of the dimension of the maximum dimension. So you have exact recovery, whatever the magnitude of L naught is, whatever the magnitude of S naught is, and there is no tuning parameter. Okay, so that's a bit surprising to people working in statistics, because usually we're used to kind of see we have this kind of algorithm where we're going to think L lambda has to balance the two terms in some ways. Here it does not have to balance the two terms. Lambda equals 1 over square root of n is universal. It works always under the assumption of the theorem, of course. Okay, so to summarize, what you do is you prepare a matrix of large rank, of rank n over log n squared, roughly. You corrupt 10% of the entries. You give it to me, and I'll tell you exactly what you've done to the low rank component. 1 over minus the probability of failure, which is 1 over n to the 10th, is arbitrary. I can put 1 over to the, we can put 1 over n to the 1000 if we want. All what that would require is to have that the rank will have to decrease a little bit. Okay, any questions about this? All right. So this morning we talked about this. We talked about matrix completion. Matrix completion is a slightly different problem. Matrix completion is you get to see entries, and there are lots of entries that you do not get to see. And arguably what we're doing now is harder. And it's harder both mathematically and it's harder information theoretically. So this theorem we've seen that if we had lots of missing data, we could recover the matrix. So that's what we've seen this morning. I'm not going to discuss it. The problem we're looking at today, this afternoon, is a bit harder because in a matrix completion, you have missing data, and here you've got corruptions. And in matrix completion, when I get to see a data point, I know it's good, so I can really build on it, if you see what I mean. In robust PC, I can't, because I'm looking at an entry and I don't know whether it's a good one or it's not a good one. So I have not only to kind of impute missing entries, but I have to detect which ones are corrupted. And it's mathematically harder to deal with this situation, and it's information theoretically harder. That is, that you can have fewer corruption than missing entries to do a good job. And so it's harder to detect and correct than just to fill in, than to impute. So this approach really works well in practice. So this is our experiments done with lambda equals 1 over square root of n, no tuning whatsoever. These are random problems, and here is an idea of how well it works. So here you see, again, these phase transition diagrams that we kind of have talked about, where on the right axis, on the x-axis, you see the rank of the low component, of the low rank component divided by n, and the right axis you see the fraction of corrupted entries. And we did lots of experiments, and then we calculate the probability of success for a given value of the rank and a given value of the corruption. And when you're in the white region, it means that you succeed 100% of the time. When you're in the black region, you fail 100% of the time. When you're in the gray region, it's 50% you succeed, 50% you fail. There are no gray regions, which means that we have a very clear phase transition between working and not working. And so what we can see from this plot is that, let's say if the rank is n over 10 and 20% of the entries are corrupted, that's no problem. If the rank is maybe n over 5, then I need maybe something like 5% of corruptions. If the rank is n over 20, then I can have 30% or 35% of corruption, and that's what this plot indicates. This is a similar plot with the matrix completion. On the x-axis, you have still the same quantity, which is the rank divided by n. On the right axis, now on the vertical axis, you have the fraction of missing entries. And that what you can see is that the white region is much bigger, because it's easier to guess what you've not seen than deal with errors, which everybody knows in error correction that erasures are much easier to deal with than errors. Okay, and so we see that this region for matrix completion is much larger. The operating region is much larger because it's an easier problem in an information theoretic sense.
What are the dimensions?
400 here. N is 400 by 400. The matrix is 400 by 400. All right. So as I said, there was this paper published by the MIT group, and the MIT group has a deterministic approach to the same problem, and they cast their result very differently. It's not a probabilistic result the way you've seen it. It's a deterministic one. And what does it say? So we're going to take as the span T and omega exactly the subspaces that we've seen this morning, where T is a span of all matrices with row space included in that of L0, or with column space included in that of L0, right? So I think, if the matrix M L was A B star, a rank 1 matrix, then this T would be for all x and y matrices of the form AX star plus Y star B. And then they introduce a modulus of continuity over this subspace, which is they're looking at the maximum entry of a matrix in that subspace subject to its spectral norm is less than 1. And then they introduce a similar quantity, which is omega S naught. And omega S naught, remember, is a set of matrices which are supported on the corruption pattern. And they introduce a modulus of continuity over that linear subspace, and that modulus of continuity now is the sup of the spectral norm over matrices in that subspace and whose maximum entry are bounded by 1. So we have two quantities which pertain to these two fundamental subspaces, T and omega, which really are the tangent plane to the manifold. This is a tangent plane to the manifold of low-rank matrices at the low-rank point. This is a tangent plane of the corruption of the S matrix at the current point. Right? These are the tangent plane to these manifolds. And what they show is that these two numbers are less, the product of these two numbers is less than 1 over 6, then the same algorithm will succeed for some lambda which is not specified. Okay, so that's a deterministic result, which is good. I think one of the issues is when is this less than 1 over 6? It's a bit difficult to instantiate, and so the paper offers a situation which is comparable to the situations we have in our papers. They say, let's assume that the maximum number of corruptions per column times the coherence of the low rank part times the rank over n is less than 1 over 12. Okay, and let's assume that the fraction, so that the fraction of corrupted entries really is the number of entries that you can corrupt, is bounded by 1 over 12 times 1 over the coherence times n times the rank. So even if the rank of the low rank component is 1, this forces you to have very small corrupted entries. That the fraction of corrupted entries is 1 over, at least 1 over squared of n. So you have, as the size increases, the number of the fraction of entries that are corrupted is going to 0 quite rapidly. But under this condition, they can show that it works. And of course, the big difference with what we have is that we can tolerate a constant fraction of corruption. It doesn't have to do anything with dimension, it's just constant. Okay, so this is a deterministic paper, and being a deterministic paper, there are very significant differences in our approaches. Even though we look at a similar problem, there are really nothing in common between these two papers. Once we state the problem, then they go their way, we go our way, and we never meet. Okay. All right. All right. So one thing that our work does in this area, it says, well, why do you have only corruption? Why don't you just have corruptions and missing data as well? Which is not addressed by this other work. And so, well, the extension is trivial, given what you've heard this morning. Suppose that now I've got only a subset of entries of which a constant fraction are corrupted. Well, I have, of course, many possible explanations for the data I've observed. I'm going to pick the one that minimizes the same convex objective. So, of course, all of this is a semi-definite program. And I'm going to minimize this convex objective subject to data constraints. And by now, you should be accustomed to results of this kind, which say that, well, if we're under exactly the same assumption as before, right, so the rank is n over log n squared at the most. If I get to see a random set of entries of size 10% times, let's say I get to see 10% of the entries, of which a constant fraction are corrupted, then the algorithms that we have at the top, with a selection of lambda, which is 1 over square root of the fraction of observed entry times the dimension, the max dimension, then we'll recover the low rank component exactly. So I can see very few entries of a low rank matrix of which of those entries the significant fractions are corrupted. I can sort out things. I can do essentially complete the matrix and correct it at the same time. All right. Okay. There's a cute thing, I think. Well, it's a very little thing, but it's kind of cute, which is that suppose you give me a matrix and I see some of the entries of this matrix, but you did not corrupt it. Okay, so like if you did not corrupt it, you just try to recover the matrix from missing entries, and in this case, what we've seen this morning is minimizing the nuclear norm is a good thing, and that will work. Okay, but I don't know that you did not corrupt it, and so I want to be on the cautious side, and I'm going to add an extra term, because maybe you did corrupt it. You did not, but maybe you have, and because I'm very conservative, I'm going to solve this problem as if you had corrupted it. Okay? And of course, what we are learning is that it gives us the same answer, that I will discover that in fact you were a good person and you did not make me miserable. Right, and so the interest of this is, of course, if there is no corruption, it's more general than what we've seen this morning. If there's no corruption, it of course will say that there are no corruption and will be equivalent to the matrix completion problem we've seen this morning. Okay, how do you prove these things? You have to construct dual certificates. The problem is it's always the same problems in high dimensional geometry with randomness, except that as you start to try to find those dual certificates, as you try to express mathematically these tangent conditions, it gets more and more difficult, and so the proofs have to become more and more involved. Okay, so I'm not really discussing how we're going to prove these things. I'm just going to show you that, well, again, it goes back to Banach space theory, and you're going to have to use through some Banach space theory to effectively show that, you know, the solution is exactly, you know, that the sparse and low rank solution are the minimizers of your convex functional, and that uses a lot of tool from Banach space theory. Okay, of course you can say in real life this is not a very valid model because you're not exactly low rank plus sparse, you're low rank plus sparse plus small noise, and it would be a shame if the theory were to collapse because you were not exactly low rank plus sparse and you could not deal with a small amount of noise, but of course you can, and so this is an extension in a paper by the same workers plus Zhu, where we showed that, well, if you have small noise, then you should not enforce that m equals L plus S. You should just have a constraint that is a bit more relaxed, and you minimize the same thing, of course. In this case, it's hopeless to think that you could get perfect recovery because you have small noise contaminating all the entries. But what you get is you get a recovery error which is within the noise level of the small noise. So in practice, this will accommodate a lot of statistical models. There are some weird things that are still, for me, a bit counterintuitive, which is that if you extra assumption on the corruption, if you say the corruption has random signs, then you can actually prove that the fraction of non-zero entries in S0 under the same conditions goes to 1. That you could not be sparse at all. Okay. And still you would succeed under the same condition with probability just by requiring that the signs be random. All right. Okay, so we know how to perform this separation. This has lots of applications, as I've seen before, and we know how to do it not only in a clean setting as being low rank plus sparse, but we can do it with small noise. So we have a robust blind deconvolution algorithm. So I would like to show you some simulations, and so the last part of this lecture is going to be a bit more easy. So we have developed algorithms for solving this large-scale problem. Maybe I will skip this part for the time being because I'm going to come back to this in a little bit. It's very connected to some of the things that Carola was discussing last night. At the moment, so let me give you an idea of the computational time. Let me give you an idea of the So we have developed an algorithm, which I'll explain at the end of the lecture. And let me give you an idea of the time it takes to solve one of these problems on something like these computers in MATLAB. Okay, so I'll show you a demo later in the lecture, but the demo will be about this line in the CPU table where I'm going to take a matrix which is 1,000 by 1,000, so 1,000,000 unknowns. The rank of the low rank component will be 50. I'm going to mess up 100,000 entries. And when we did these experiments many times over, each time we recovered a rank which was exactly 50, a cardinality, a sparsity pattern which was exactly 100,000. When we look at the numerical precision of the low rank component, we've got 6 digits. And the time it takes on this laptop to run a problem of this size is about 13 seconds. So 13 seconds might not tell you much. I mean, you're solving an optimization problem with 1,000,000 variables, so 13 seconds is not bad. I think the better unit of time is the number of SVDs that it takes. And what we find consistently is that to run this algorithm that minimizes the nuclear norm plus the 1 norm takes about 15 times the number of SVDs that it would take to run on a problem of the same size. So if you can afford principal component analysis, which would take 1 full SVD, then you are 1 order of magnitude away from this thing. Okay, so that's not, it's higher than classical principal component analysis, of course, but not by a huge factor. Okay, So there is a person I never talked about during these lectures. That's my wife, and she's a statistician, and she's very skeptical of some of the things I do. And she says, you know, these tables, it looks good because what you did, Emmanuel, is you took a very, you actually, she thought that what we had done was that by just looking at the entries, I could tell where the sparse component is and where the low rank component. So for example, if the low rank component has magnitude, I don't know, 1, and the sparse component has magnitude 10 million, just by thresholding, I would be able to separate them. Okay? And so she said, I'm going to prepare an example for you that makes your life difficult. And she did this. So she said she prepared a low rank component by some randomization methods. And because she used random factors, the distribution of the entries is Gaussian. And she prepared a sparse component such that the amplitude of the sparse component was, you know, the low rank component had all of its coefficient between -4 and +4, and the sparse component will be just plus or minus 1 on top of this. So when you look at the histogram of the sum, it would not look that different from this. Okay, and so sure enough, that's how the beginning of Chiara's matrix looks like. You see the first 100 rows and 100 columns, color-coded, so that red is +4, blue is -4. And if you see the sparse part in here, I'm impressed. Okay, and so M, that's the first 10 rows and 10 columns of Chiara's matrix. And in fact, the low rank component is this, the sparse component is this, but of course you don't know this. And you run the algorithm, and sure enough, it finds the low rank component and the sparse component with no error because there's nothing in my theorem that depends on amplitude. All right. Now, Chiara's example was a bit more time consuming than about 15 SVDs. It was more like something like 25 iterations. We'll see that we have an iterative algorithm, like it took about 22, 23 iterations, so maybe 20 times slower than a regular SVD. All right, and then when you look at what the algorithm does, first of all, we were estimating the low rank component, the rank started to increase, and then boom, it decreased, and the sparse component had this pattern.
Does this sort of solve the problem of stenography and detecting watermarks in pictures?
The problem of?
Stenography, where you hide some information in a picture. It's, you know, you can watermark a picture.
Yes.
One sim, for example, it's
Yes.
watermarked, so you
Do you have low rank structure somewhere?
write well. That's it. Yeah, probably not.
I don't know. I mean, it's an error correcting code. That is for sure. That's an error correcting code. Yes.
So you said your results didn't depend on the magnitude, but what about the one with the noise?
They do.
Yeah.
They don't do. I mean, they what you do is you recover the entries to within the precision of small noise. But it does not depend on. It's not because S is big that you cannot recover L well. If small noise is small, the error will be small. If small noise is big, the error will not be small.
So if S is small, then you can just say 0 and then you're fine.
Yeah, sure. But this has to do, what we're after, remember, we're after, things where things go completely wrong, right? Like you really don't get the right projection at all. All right, so where were we? All right, so now we're going to have a bit of fun because my colleagues, they take this and they run with it and they develop what I call cool application. Well, I think they're cool applications, I'll show you. Okay, so first of all, the separation problem. And so here is the problem I discussed before. We want to separate foreground from background. And so we're just going to apply this algorithm out of the box with lambda equals 1 over square root of n. First of all, note that for this problem, this assumption of the theorem do not apply because the people who move about the low-rank background, it's certainly true that their entries of the sparse component are not randomly sampled. They are highly structured, in fact, because they are contiguous. But nevertheless, it's not going to stop us from applying this thing. And when we apply it, it seems to work very well. So this is 3 frame out of a sequence that has about 2,100 frames. So I show you 3 frames. Right? Here you see the low-rank component that looks like background to me. Here you see the sparse component that looks like people moving about the airport. That is after you do background subtraction. All right? And you would say, well, what is this person doing here? Well, this person has not moved. So as far as I'm concerned, it's background. It could be a statue. Right. Here you have a competing approach which has some problems with these plants. Okay, and you can see that, it's messing up the people moving here and things like that. Where for us, I mean, it's a bit what Carola was talking about, this in-painting thing. Except that we use a completely different structure for doing it. We use low rank, well, she used sparsity in some basis. But, you are really, you take these people, you remove them, and now you can actually put the texture right behind. Right. And why can I do this is because I have other shots. And I use a low-rank background and the fact that all these shots are highly correlated to be able to do this, right? But here you really remove people and you actually put the right texture. This guy was in front of this thing and you see them here. All right. This is a more interesting example. This is a scene taken from a lobby. These are all standard examples that people in computer vision, they have to, in medical imaging, log and ship. Here, there's a database where you have to do well on it. All right. It's less and less true, in fact, the log and ship. It used to be cool, but it's a bit 90s. All right, so this is taken in a lobby, and what's nice about this sequence of images is that you can see the light intensity is changing with time. Lines are being turned on or off. And so light intensity, that's why the background is not rank 1, because the light will change. And so it will illuminate things differently. And the algorithm just decomposes this sequence of images as low rank plus sparse. Here we've got the sparse part, which captures this guy who at some point walked into the lobby. This is a kind of what my colleagues tell me is the state of the art in this area. This is the competing algorithm, and you can see that they have problems with the foreground and the background. My business is not to say that it's better than what other people do. My business is you take a very simple thing, you apply it out of the box, and without any tuning, it does well, which is surprising. People do, okay, so people, are you interested in face recognition? Are people interested? Yeah, okay. So face recognition, in a way, it's almost a solved problem if we were in highly controlled conditions. So if I stand in front of a white wall like this, and there's somebody taking a picture of me and I never move, and my head is always inside the square and everything, and I have pictures of this whole room, and I have 100 pictures for each of you in a very controlled condition, where you fit in a square and so on, we kind of know, people have developed methods that work well. The problem is, of course, nobody is in a controlled condition, and you've got various problems when you take real data because you have shadows, you have saturations, which makes the algorithm fail. Because of these non-idealities, the fact that we're in an uncontrolled environment, the algorithm would look for some cue, do not apply. Like, let's say I look for your eyes, but you wear sunglasses, and what am I going to do? Okay. So the idea is to use this as a pre-processing step for a more elaborate classification. Okay, so then we're going to try to find, to remove shadows, specularities, everything that essentially confound these face recognition algorithms. Right. And so when we apply this to real images, like for example, you take images of the same person, but you see very strong shadows, like the eyes are not, you can't see them anymore, or here the camera saturates, I don't know if you can see this, and then you apply this low rank plus sparse decomposition, and so the low rank part removes some of these effects, and of course they show in the sparse components. Okay? So for example, we've got these well-known specular points which appear in the sparse component that have been removed, the shadows which are strong have been removed, and of course they all show in the sparse component. Okay, and so now you can clean up these images and apply recognition algorithms to the low-rank component. My colleagues, now this was our joint work, and now this is not my joint work anymore. This is just the work of my colleagues for a few slides. Of course, the ideal application of these techniques is to clean up old movies, which is the ideal application, where you have a collection, you have a sequence of frames, and of course we all know that old movies look like this, but that's extraordinarily amenable to this technique. The low rank part is your denoised image. And so we've got things here that are completely gone over here. We've got speckles that disappear because they're sparse, so they go in the S-sparse. We've got lines that are completely gone. You've got lines that are removed. And it's automatic, you don't have to specify anything. You have lines that are gone, speckles that are gone, and so it really cleans the movie quite well. One thing you have to be careful though is the way you tune parameters, because if you remove Tom Cruise, that's not so good. Okay. It's been a long week, so we have the right to be a bit more. Okay. All right. Now this is really it's a different world. It's not the math world we are in anymore. It's just people doing things and seeing whether they see good results. So in general, I can try to convince yourself, and it's not going to be very difficult, that if I take images of faces, then my low-rank plus sparse model will not apply. And the reason it will not apply is that if you're not centered, then of course the fact that we can have shifts and so on, or maybe the camera moved a bit, means that because I don't have perfect alignment, I'm not going to see low-rank plus sparse. So maybe my model is correct only after some rigid or projective or affine transformation. So what do we do, or what do my colleagues do? From Microsoft Research, what they do is they say, well, why don't we just try to do everything at the same time? Let's try to find a deformation such that after deformation I'm as low rank plus sparse as possible. So now you say, you look at this, wait a minute, it's not a convex problem anymore. It was convex if the deformation is fixed, but you have tau now as a deformation is also a variable. So it's an optimization variable. Now we're not looking at a convex thing by no means, but we can still solve a sequence of convex programs. We solve for tau, we linearize, we do gradient descent, we do stuff. Okay. All right. So the idea is to not only to find for L, S, and tau simultaneously, so that at the end of the day, I've got something as low rank plus sparse as possible. What it can do is a bit surprising. So here is you've seen shots of a building from different angles, with sometimes a tree occluding it and sometimes not. And so if I were to try to use this as a low rank plus sparse, I would not do well because there's a difference in perspective. But now I fit tau, low rank, and sparse, and I look at them. First of all, that's a fitted deformation, so that's the images after registration, so it's going to align the geometry. And then I look at the low rank part, and it seems that it's what I want, and I look at the sparse part, and I see the trees, and it seems that it really works well. Okay, we can do this with videos. I'll skip this. Here's an interesting thing. If people are interested in character recognition, so this is like you're given a table of training set that are number 3s. And what you say is like, what if I could run low rank plus sparse with a deformation, right? Because of this kind of deformation, things might not be exactly low rank plus sparse, but after you fit this model, you've got the deformation, then you've got the low rank component, and I claim that doing character recognition on images like this is not going to be very difficult. And then you have the sparse part that is a mismatch between the low rank component and the sparse part. To me, the most puzzling example is this one, where now we have pictures of a person, and I hope you can see this image so we have a picture of a person, but you can see this person is under severe conditions. So let's say same person. This person is wearing sunglasses here, is wearing something in front of his mouth here, a wig, a hat. His hand is in. Can you see this thing? His hand is in front of his mouth. Very strong shadows. He's shouting, things like that. Okay. And now you run this deformation model, low rank plus sparse, and you look at the low rank part. And it seems that you've recovered your person. Like the sunglasses are here, the hat is here, the wig is here, the hand is here. And you say, you know, good luck for doing face recognition on a guy like this. But this guy, you actually recovered it as this, and now you can tell who this person is. Okay, so it's really quite, to me, surprising how well this model works on highly non-idealized data, on real stuff. And it's, again, pretty much out of the box. Like one thing we don't use, which we should use, is that in video, for example, we know that these are pixel images, so the lowering part should be non-negative. But we don't even use that. I mean, non-negative, that every component of the lowering component, these are pixel intensities, so they cannot be negative. So we don't even use that. So there's room for improvement, of course, but I think what's more fun is to see what it can do already as is. Okay, so you don't have to stop to all these applications, you can do lots of things. So if we look at textures, we could have textures. So, all right, so here are textures. And of course, these textures are not low rank plus sparse, but if you could actually transform them, perhaps by rigid motion, then you could align this texture so it looks like this. This is extraordinarily low rank plus sparse. In fact, it's low rank. In a texture like this, once you deform it, it will become like this. It's a very low rank matrix. Texture will become like this. This become low rank stuff. So people are trying to find the transformation that gives you on a single image the most low rank plus sparse decomposition. And when you apply it to things, it does really nice things. So for example, you find actually the perspective. Right, so you take a texture like this, you find the low rank and sparse component. Of course, in the middle, you find the projective transformation so that can realign the textures. When you're doing this, you realign things like this. To me, these are things that are very, very nice to see. Here it's a signpost with Chinese characters. And then, of course, everything is slanted, so now you run this algorithm and it will unslant everything. This is a piece of paper that is, of course, slanted. You run the algorithm so that you're low rank and sparse, and it's like if you're having it in front of you. So you can do lots of things, and people sure do lots of things, are quite excited about it. So you can move the piece of power. That's a good idea. I mean, this thing I really find impressive. Like, you want to do character recognition, but you have this perspective effect. And so you undo it by this simple algorithm, and all of a sudden you can recognize those Chinese characters, and so on and so forth. So there are lots of examples. Of course, because you're undoing the projective transformation or the affine transformation, you know the orientation of surfaces, which for people working in computer graphics is nice, because then you can map things onto surfaces and things like this. So I hear from my colleagues in computer vision that these tools find a lot of applications. Lots of people are excited about it. It's also a community that is periodically very excited. All right. Okay, so let me talk about, in 10-15 minutes, computational aspects of RPCA. So as I said before, we developed an algorithm for solving these things, and if this computer works, maybe I'll try to show you maybe a little demo in MATLAB to show you that we can do this. So basically what I'm going to try to do is the table you've seen already, and I'm going to try to show you something along this line. Okay, all right. So first of all, now maybe it's not going to work. Yeah, so first of all, I'm going to show you the thing on a simple problem, right? So this is going to be a simple problem. I'm going to take a matrix which is 60 by 60 on a small problem. Take a matrix which is 60 by 60 of rank 2. I'm going to make a low rank component by multiplying two factors which are 60 by 2 and 2 by 60. Then I'm going to take 1% of the fraction of the entries. I'm going to mess them up. And then I'm going to show you the sum. I'm going to set lambda equals 1 over square root of n. And now I'm going to invoke this magical CVX, which I'm going to solve the problem we've just seen. Minimize the norm of the nuclear norm plus lambda times the sum of the absolute values of S subject to L plus S equals n. Okay. All right, and so as we've argued today, what the stuff is doing, it's solving a semi-definite program, which you see being solved. So semi-definite programs are a very large scale. And so this is using an interior point solver to solve it. And okay, so in a little bit that's going to be finished. Okay, and of course now we hold a guess of what L is, and what we're going to want to check is the relative error on the low rank part and the relative error on the sparse part. So I'm going to compute the relative norm L minus L0 divided by the norm of L0, the same thing for the sparse part. And if everything goes well. All right, okay, so we've got them here. So we've got a relative error on the low rank part, which is 10 to the minus 11, on the sparse part, which is 10 to the minus 10, so that's pretty good. Now, the thing that I just want to emphasize, and what I emphasize in the theorem is, now what I'm going to do is I'm going to take S0 and I'm going to multiply it by 1,000. So I'm going to really increase the size of the corruption by 1,000. And intuition tells me that I should rebalance the two terms in the optimization, but I won't, because I'm not resetting lambda to be 1,000 divided by square root of n, something like this. See, I don't reset lambda. Lambda stays 1 over square root of n. And so now I'm going to just, the size of the error has been increased by 3 orders of magnitude, but the problem does not change. Lambda does not change. Still 1 over square root of n. Does it do something? Yeah. Okay, so lambda does not change, and then we have to wait for the output. But what we're going to see, if everything goes well, is that I did not change anything in the optimization problem, even though S was getting 3 orders of magnitude bigger. I did not try to rebalance the two terms. And CVX is using an interior point solver. Okay, so now I've got, it's still exact 10 to the minus 9. And the point of this thing is that the algorithm did not change. Now, of course, we don't use this because this uses an off-the-shelf interior point solver. We develop our own method for solving it. So now we're going to look at this algorithm that we propose, which on an example now we're going to do more interesting things. N is 1,000, the rank is 45. I'm going to mess up 100,000 entries, so I need to solve a problem with 1 million unknowns and 100,000 corruptions. And so it's generated in exactly the same way. All right, and now what I'm going to do is I'm going to just invoke this algorithm we have, which is called RPCA, that takes as input nothing but the sum of these two matrices, because it's going to assume that lambda is 1 over square root of n. All right, and so this is our algorithm. We see that it is an iterative algorithm. After 2 iterations, it has discovered that the rank was 45. that it thinks that the number of errors is 300,000, but then it's going to adjust it very quickly, and after 5 iterations, it has a correct rank, the correct 5 or 6. 5, it has a correct rank, the correct number of corruptions, and then it's improving the solution. And so this finishes in about 14 seconds, and this is a MacBook Air, so it doesn't have a very fast processor at all. And so what we can see is that I can solve an optimization problem, at least this optimization problem, in 14 seconds. And then I look at how good is the solution. The solution has 6 digits of accuracy. Right, so I can solve these problems with 1 million unknowns in about 14 seconds on this computer. And so essentially the number of times I took an SVD is roughly 16. So it's about the same cost as if I had computed 16 SVDs.
What was N for just the previous demo with CVX?
60. Like now N is 1,000. So before we had 3,600 unknowns. Now we have 1 million.
Is there a limit to the order of magnitude of the perturbation in S?
No.
S is epsilon, for instance.
No. That's weird, huh? But no, if S is 10 to the minus 80, I will say that S is 10 to the minus 80. Okay, so I have other demos for matrix completion. You want to see a demo for matrix completion or not really? Maybe no. Maybe we see a demo for matrix. You're the boss, Ben.
Yeah, that's
Okay. So I have also a demo for matrix completion. This is what we've seen this morning. So now we're just going to minimize the nuclear norm. There is no corruption. And okay, so that's what we've. Now we have another algorithm to minimize the nuclear norm and the nuclear norm only. So this, I don't want to show you small scale. I want to show you just large scale stuff. So you can reproduce this. I can also put this on my the place where I put the lecture notes, so that if people want to reproduce this, they can. Okay, so what do we do now? We've got a matrix which is 1,000 by 1,000 of rank 10. It's just a random matrix. The number of degrees of freedom, as we calculated this morning, is R times the sum of the dimensions minus R. I'm going to show you 5 entries for degrees of freedom, no more. Okay, omega is going to be a random set of size m selected around n1 and n2. The data is simply the value of m on omega. So that's what we're going to do. All right, and now we're going to solve another algorithm, which is we call the singular value thresholding algorithm, which will take as input the data, the location of the entry, some parameters, and is going to try to guess by just minimizing the nuclear norm what are all the missing entries. It's also an iterative algorithm. Okay, that tells me that I use a small, not very fast version of MATLAB. And so you should probably cut down the time by a factor 2 or something. But basically, after 18 seconds, minus the time it takes to print these messages, minus the time it takes to run MATLAB code instead of C code, it's 18 seconds an hour, but of course maybe I hold something that is no good at all. So let's see the relative error on the place where you gave me data. So this should be 0, of course, and on the place where I did not have data on all the missing entries. So let's look at the relative errors. Okay, so got net 4 digits of accuracy, because this is actually an algorithm that does not stay always feasible, but it's eventually feasible when it converges. The relative error is in the Frobenius norm is 4 digits of accuracy. In the spectral norm is also 4 digits of accuracy. So you guessed. So I show you 100,000 entries, probably 5 times the number of degrees of freedom. So let's look at this. Right, so n1 plus n2 is 2,000. The rank is 20,000 times 5. I showed you 100,000. I had to guess 900,000, and I had 4 digits of accuracy. It's about 15 seconds, and this is really not a good laptop. I mean, It's a very good laptop, but not a high-powered laptop because it's there's a MacBook Air. Okay, with a slow processor. All right. All right. So these algorithms seem to work well. And what do they do? All right. So maybe I'll show you the first one. Maybe I'll show you the. Well, we have two algorithms. How much time do I have? 10 minutes. Maybe I'll show you the matrix completion algorithm, which is kind of more enlightening. Maybe you can see. Right, so this is a part that this morning we had to skip. All right. So let's suppose I do matrix completion, and let's say I want to minimize the nuclear norm of x subject to the projection onto omega of x. So p omega is what I explained this morning, is xij if the entries is observed and 0 otherwise. So let's say I want to minimize the nuclear norm subject to the observed entries matched. Okay, so we're going to introduce a very simple nonlinear operator, which is a singular value thresholding operator. And the singular value threshold operator is very simple. It gives me the SVD of a matrix. And what I'm going to do is I'm just going to push down the singular values by tau. So it takes as input a matrix, it computes its SVD, and it shifts towards 0 the singular values, but they should not become negative. So it's a maximum between sigma j minus tau and 0. But so what it does, it applies, I think we've heard this in Carola's talk and in Vincent's talk, it applies soft thresholding to the singular values. Of course, this is a rank reducing operation, and the algorithm will essentially do this. Now the algorithm is very simple. You start with y naught equals naught. You fix a tau which is positive and a sequence of positive step sizes. You start with y naught equals 0 and you inductively define for k equals 1, 2, 3. You take yk minus 1 and you apply this shrinkage operation where you threshold the singular values of y. Okay, so you keep the singular values above tau and you set the others to 0. You lower the singular values above tau by tau and you set the others to 0. And then you update y in this formula. Okay, now y, as we can see, y is 0 at the beginning and y only gets updated onto the visible entry. So y is always a sparse matrix with always the same support, which is a location at which I have data. So it's y is always a sparse matrix. And I do this until convergence. This algorithm is not really novel. It's essentially something called an ascent algorithm on the dual side. We're inspired by lots of work in optimization. There's really nothing really new about this. We were inspired by Bregman iterations in compressed sensing, by iterative thresholding algorithm for sparse recovery. It's a natural extension of this framework to the matrix world. But it's really a Lagrange multiplier algorithm. I mean, if people are specialists, they will recognize that this is a dual update, that y is in fact a dual variable that is updated in the direction of the gradient of the dual function. Okay, so why do we like this algorithm? We like this algorithm for two reasons. Number one is you ask me to lower the singular values of a sparse matrix. So now I have to do an SVD of a sparse matrix. That's a good situation. SVDs are expensive, but if the input is sparse, that's good. Now there's something which is and of course it produces the solution we want. So maybe I'll skip this, but of course this algorithm, when it terminates, is actually not exactly solving your optimization problem, but something which is very related to it. And I think it minimizes the nuclear norm plus 1 over 2 tau times the Frobenius norm squared subject to the data constraints. Okay, so that's what it solves, and when tau is large, this term is negligible compared to this one, so it really minimizes the nuclear norm. All right, so it converges to what we want. But what I think is interesting, and the reason this algorithm is interesting and so rapid, is that what you look at the rank of the iterates as the iterations goes on, what you see that the rank starts to be 0 and then it increases. So if the true rank is 10, it increases very rapidly to 10 and then it stays there. If the rank is 50, you increase rapidly to 50 and then you stay there. If the rank is 100, it increases rapidly and you stay there. And now why is this good? Well, if the rank is monotone, which we cannot prove, but suppose the rank was monotone during the iteration, and suppose the solution has low rank, then all these iterates xk, you see their ranks here, they all have low rank. So what do I have to do then? I have to calculate only the top singular vectors of a matrix that is sparse. And that's the best situation I can think of, because I only need to compute a few singular values of this input yk minus 1, but yk minus 1 is sparse, so Langström iterations are going to be extremely effective for doing such a thing, and that's why the algorithm works so fast. It's because at each iteration I need to compute only a few singular vectors of a very sparse matrix, and there's extraordinarily good software for doing this. We use a software package written by Monk Larsen called ProPack that is very good at calculating the top singular values of a matrix. And here we use sparsity, of course, to speed up the calculations. Okay, we actually, for fun, with my grad student Stephen Becker, we implemented this on we wrote down a parallel C implementation on a 4-core CPU to give you an idea of the problem size we looked at on a single machine, 4-core CPU. We had 30,000 by 30,000 matrix of rank 10, so we're close to 1 billion entries now. We observed 4.4% of these entries. We solve this, we run this algorithm, and we get the 4 digits of accuracy in something like 3 minutes and 15 seconds. And it's because we're in this very favorable situation. Okay, so I'm going to return to lecture 7. For the robust PCA, we have decided to use an augmented Lagrangian approach, where essentially we write down our optimization problem as we're going to augment it by, it's a standard trick in optimization to augment the objective by something which is 0 at the optimal. This is called an augmented Lagrangian approach. All right. Then we form the Lagrangian. So we have this dual variable y, and a standard dual method in optimization would just essentially maximize the dual function. And so a dual gradient ascent algorithm essentially minimizes the Lagrangian over L and S for a fixed value of the dual variables, then take a gradient step in the direction of the dual function, takes a step in the direction of the gradient of the dual function, but the gradient of the dual function is just this. It's just the constraints. So it updates y in a very, very simple fashion. And so that would be a very standard algorithm for doing this. Now the problem is that this is very difficult to do. We don't know how to do this in closed form. But a little bit like what Carola discussed yesterday, we have these 2 operations, which are the component-wise thresholding and the singular value thresholding. Right? Singular value thresholding algorithm is simply lowering the singular value of the matrix. Component-wise thresholding is doing the same, but on the individual entries. And the point of this is that it's easy to minimize over L and S separately, because the minimizer over L is a prox function of the nuclear norm that's given by singular value thresholding. The minimizer over S is given by the prox function of the one norm, which is entry-wise soft thresholding. And so what the algorithm does, it minimizes over L, then it minimizes over S, then it updates Y, then it minimizes over L, minimizes over S, and updates Y. And so what the algorithm does, it takes this matrix, shrink its singular values, update L, pass it here, shrink the component of L, and just update Y. And so the whole algorithm is here, which doesn't take very long to code. And so it's essentially all the computational cost is here in shrinking the singular values of this matrix. But of course, if all these arguments have low rank after self-thresholding, then you really only need to keep and compute the top singular vectors of this matrix, and therefore the length iterations are going to be very effective. And that's why these algorithms scale pretty nicely to high dimension, in high dimensions. There's of course a lot of research in trying to make this better.
How stable is
It's because you have an augmented Lagrangian approach, it's kind of stable, right? Because of this term.
it? Because Langros need not be stable.
Yeah. All right. Well, Langshos, so maybe I misunderstood your questions. Typically, people who minimize non-strongly convex functions are worried about stability. And the augmented Lagrangian is a way of stabilizing the computation. But I think you use a different kind of stability in the Langshos algorithm itself.
Yes.
We don't see much problems, but maybe it's because maybe we just don't do problems that are so hard. I mean, I don't know. Okay, so last 5 minutes on large-scale optimization. So compressed sensing, as I said at the beginning, has 3 areas of main activity: theory, algorithms, and applications. What we have not discussed during these lectures is that we'll see what happens with CS. Maybe it will die, maybe it will not, we'll see. What will not die for sure is that people will be interested in finding sparse solutions to underdetermined systems for sure. And so what we see in CS, motivated by compressed sensing, is we see lots of algorithms for solving sparse recovery problems, L1 problems, nuclear norm problems, etc. And then there's a huge outpour of research in trying to get very fast methods for solving these very large scale problems. And so many people contribute, and I cannot list them all. And really the field has really advanced in the last few years, essentially under the leadership of Yuri Nesterov, who introduced some very pioneering ideas for non-smooth optimization in 2005 and in 2007. All right. Okay, so it's all the rage at the moment. It's a fairly competitive field. The same is true for nuclear minimization. You have new papers telling you how to minimize the nuclear norm almost every day. L1 is the same. I cannot report on this outpour of work, but what is for sure is that now we know how to solve L1 problems faster and faster and faster. And we're in a complete different situation than we were 10 years ago. And for example, OSHA has done some very nice work. There's really lots of people contributing to this field. Recently, I have been working with a colleague of mine by the name of Michael Grant, who is a person behind CVX with Stephen Boyd, and with a grad student of mine named Steve Becker on templates for convex cone programs. And so our approach is slightly different. And we are trying to develop something which is similar to what happened in numerical linear algebra about 15 years ago, 20 years ago now. 20 years ago, in 1987, I believe, there was an influential book that was written called Templates for the Solution of Linear System, Building Blocks for Iterative Methods. And the idea of these people was to provide building blocks for constructing linear system solvers. And so the templates were introduced to meet the needs of both the traditional user and the high-performance specialist. And templates are a description of a general algorithm rather than just an executable code that you would find in MATLAB or in a conventional software library. So that if you know something about numerical linear algebra, you can actually use your templates to assemble a solver yourself. So you can pick your preconditioner, pick your CG solver, pick whatever you want, and then assemble things like this. And what we've tried to do is we've tried to do something similar for convex optimization, and that's a significant software engineering effort that has really been made possible by Michael Grant and Stephen Becker. So we have actually a release code by the name of TFOX, which is Templates for Convex Cone Programming. And there's a website where you can download the code for free if you work for a nonprofit organization. And the inspiration is, of course, to kind of reproduce what these templates did for linear algebra in the world of convex optimization. All right? And so the primitives that we have underlying our methods are the same, essentially the same primitives, some of the primitives that the templates have, which is BLAS, block multiplies, etc. We have the same primitive. Of course, we have other things which have FFTs, conic projections, and so on. But basically, we're not going to bother with these things. We're going to assume that your manufacturer takes care of this thing, takes care of BLAS, takes care of FFTs. We're just going to leverage this thing. And the point of these templates is essentially to kind of create all these different routines that would let you assemble a complete solver for any problem that we've discussed in these lectures, including some of the best solvers that have been developed over the last 10 years. And so we've included in TFOX all the state-of-the-art methods that we can think of. That includes lots of Nesterov methods. Carola mentioned Fista yesterday. It's also in there. So we've got lots of different solvers that are actually built into TFOX. TFOX is just not implementing the solver. It comes with a lot of important tweaks that make convergence faster. And basically, you can use it very efficiently. You don't have to find out what is the best step size. We have lots of step size rules that you can choose from. We have restart methods. We've got everything that goes in convex optimization. And so the idea is that to provide something that is friendly to use and lets you experiment with lots of different methods. All right, so with TFOX, you can actually do things that CVX cannot do. You can solve very large-scale problems. Again, we can solve problems with the millions of unknowns. We can denoise large images using a number of algorithms that you'll find in TFOX. And so, again, the point is not to say we have the fastest method, it's to provide users with lots of proven methods that you can use to solve any problem you like. So we have not seen a problem in this lecture that TFOX cannot solve. In fact, it can solve much more than what you've seen. Maybe I'll skip all these things. It implements first-order methods, but first-order methods have been associated, have a bad name. They're supposed to be slow, but there's been so much progress in the last few years due to essentially Nesterov and the smoothing techniques and so on. And TFOX builds upon this to make something that is usable. Okay, so my last slide would be something like this. If you play with TFOX and you say, let's solve an L1 problem of a kind of a large scale with TFOX, that is something that comes out of the box, how long will it take? All right, so let's say I have N is 250,000, 260,000, so I have 260,000 unknowns. And I think this is a problem where, so what is the problem here? We try to minimize the most basic problem. We minimize the L1 norm subject to AX equals B. And what is A discrete cosine transform? A subsample discrete cosine transform is something which comes with a fast vector, a matrix vector multiply. So let's say we have a problem with 250,000 unknowns, and we're going to run this on a laptop, a Pentium i7 processor, quad-core, 64 bits. All right, so we get 4 digits of accuracy, which is for most applications I'm familiar with, is more than enough, in about, I don't know, 6 seconds or something like that. Of course, the solutions for problems of a smaller size are almost instantaneous. And as the size increases, we see, of course, as you can expect, a linear degradation in performance, just essentially the algorithm scale like a constant times n. And so if we look at the problems with a million unknowns, which starts to be pretty large, the amount of time I would wait to essentially get 4 digits of accuracy is not 6 seconds anymore, but 25 seconds. All right, so just to conclude, I would like to say that, roughly speaking, a lot of the algorithms you've seen, if we are in the L1 world, whether we solve the Danzig selector or the lasso, or things that are with exact equality constraints, it is rare for me. I mean, I don't think I have seen instances where I need, using TFOX or other like algorithms, to apply more than, I would say, 2,000 or 3,000 times the matrix A or its transpose. So if you can afford 2,000 matrix vector multiply with your A, then you can solve this problem. Right? So the time it takes, and I think that's a bit of the slogan in the community at this point, is that the time it takes to solve the lasso, for example, is 1,000 at the most matrix vector multiply. So if you are an MR where your matrix is an FFT, we're talking 1,000 FFTs. But it's usually less. But it's at the most 1,000 FFTs. That's roughly where we are at the moment. We are somewhere around 500, 1,000 FFTs for solving lasso-like problems, Danzig selection problems, or problems of this kind. Okay, in summary for this lecture, I showed you a principled approach to robust PCA that works well in theory and in practice. We have an idea of how this might be implemented, but I'm sure people will do much better. There are many applications of these low-rank plus sparse separation problems. I've shown you a few, but there are many more to come. Thanks a lot.
In your theorems, I think you were assuming that the sparse positions were random.
Mm-hmm.
It didn't seem like in application, of course, they're not random. They're
And I
clustered.
think
It didn't seem to hurt in the application. But do you have theory now for that?
Yes, there's a new paper by Sham Kakade, people at UPenn. Kakade, Zhang, I forgot the third author, I think he's Su, who have extended this to deal with to remove the randomness. The results are weaker, but there's no random assumption on the sparse component anymore. Yep. It's a field in rapid development, but there are results for deterministic patterns. They're not as strong, but they're pretty good.
No further questions are.
How crucial is this parameter lambda equals 1 over square root of n?
Oh, it's not crucial. I mean, there's a whole range that works. In practice, you should play a bit with lambda because who knows whether the assumption of the theorems are valid, right? But what we found in practice is that to start with lambda equals 1 over square root of n and explore around this value is a pretty good idea. So we found and my colleagues especially have found few applications where lambda needed to be it doesn't really happen that lambda needs to be, within a factor 10 of 1 over square root of n. That's always the area where it likes to be. Maybe a bit smaller, maybe a bit larger, but by no more than a factor 10 in each direction.
Since we're a little bit over time, maybe we stop here for the moment. So we're going to reconvene at 4 for a talk by Anders Hans on infinite dimensional compressed sensing. But let us thank Emmanuel again.